I think we should start, Gaurav.
Okay, fine.
Okay. So good morning, good afternoon, everyone. Welcome back to another camp day of limit, last day of the limit camp. And today we have Gauransh Kapur with us. He is interested in algebra and number theory to be very broad, and he will be speaking about what is the topic? I just forgot the name. Could
Yeah,
you
like,
just
yeah.
yeah, binary quadratic forms, primes producing polynomials, and class number one problem. So over to you, Gauransh.
Thank you, Shivaji. So I hope all of you are enjoying Limit until now, and I hope you enjoyed this talk too. So as you can see, the title of my talk is Binary Quadratic Forms, Prime Producing Polynomials, and the class number one problem. So before we go into any major theory, let's begin with a simple exercise. So this is a theorem which states that there is no polynomial p of x with integer coefficients which outputs prime values for all integer inputs. So would anybody like to suggest how we can try to prove something like this? Okay, so anyway, let me show the proof. So let's assume p of x is an integer polynomial. That means we can write p of x as a n x power n plus a n minus 1 x power n minus 1 plus so on until a0 where ai's are integers. So we're assuming that there is some polynomial which takes on prime values for every integers, and we'll show that this will give us a contradiction. So putting x equal to 0, we must get a prime by hypothesis. So this means that p of 0, which is a0, must be prime. And now if you put any multiple of a0, so if you put x equal to a naught times n, then what you'll notice is that p of x, which is p of a naught times n, will have all of its terms divisible by a naught, right? Because, so I'll just take this m, because the first term is a n, a naught m whole power n plus a n minus 1, a naught m whole power n minus 1 plus so on, and the last term is a naught. So this is divisible by a naught, this is divisible by a naught, and this is also divisible by a naught, which means that this entire quantity p of a naught times m is divisible by a naught. But we're assuming that it gives prime values for everything. So this means that p of a naught m must be plus or minus a naught for all m and z. Otherwise, it would be a multiple of a naught and it would contradict that this is prime. So what this would give after squaring both sides is that p square of a naught times m minus a naught square equals 0. So this is a polynomial of degree 2n, and what our hypothesis is showing that this should be true for all m and z. So what we are getting is a polynomial equation of degree 2n which has infinitely many solutions, but we know that any polynomial over C will have finitely many zeros, so this is a contradiction, and hence we are done. So this was a little appetizer to begin. So if anybody has any doubts in the proof, you can feel free to ask. Okay, so moving ahead. So now we ask, is there a prime, is there a polynomial with integer coefficients which takes on infinitely many primes? So the answer for this is in fact yes, and it is due to the following theorem of Dirichlet, which is called Dirichlet's theorem on primes in arithmetic progression. So the theorem is as follows: if a and b, n, well, it's not n but z, but it doesn't matter. So if a and b are co-prime natural numbers, then the arithmetic progression a plus nb contains infinitely many primes. The proof of this is, well, very non-trivial, so we leave that. And from this, we can easily see that this polynomial a plus nb for co-prime a and b will give us infinitely many prime outputs. So today we look at polynomials which produce consecutive primes, and one of the famous examples of such a polynomial was given by Euler. And I'm sure some of you might have seen this example before. So this is the example. The polynomial was n squared minus n plus 41. And what happens here is if you put n equals 0, you get 41, which is prime. If you put n equals 1, you get 41. If you put n equals 2, you get 43. N equals 3, 47, and so on. And until n equals 40, you get 1601. All of these numbers are primes. But if you put n equal 41, you get 41 square, which is obviously not prime. But what is remarkable is that this is a polynomial and 41 consecutive values it's giving out are primes. So we naturally ask, are there any other polynomials of this type, and is this the largest one? The answer is actually that this is the largest polynomial in the following sense, which is given by this theorem. So this states that the polynomial n square minus n plus c is prime for 0 less than equal to n less than equal to c minus 1 if and only if c is 2, 3, 5, 11, 17, or 41. So these numbers are they seem to be very random, and this is a very small set. So today we'll try to see why these numbers appear and what these numbers exactly are. That's the goal of this talk. We won't be proving this theorem, but we'll see why these numbers appear and what they're doing exactly here. So let's begin by introducing binary quadratic forms. So a binary quadratic form is a function f of xy, ax squared plus bxy plus cy squared, where a, b, c are in some set k. For today's talk, we'll take k to be the integers. We define the discriminant of f, as you have seen before, is delta of f to be b square minus 4ac, and we associate a matrix to f given by mf, which is 2a, b, and 2c. So if we find the determinant of this matrix, it's 2a times 2c minus b square, which is 4ac minus b square, which is exactly negative of the discriminant. And we say m is represented by f if there are integers x and y such that f of x comma y equals to m. We say f of x y equals ax square plus bxy plus cy square is primitive if the coefficients have GCD 1. And we say f properly represents m if any representation of m with f of x y equal to m implies that the two numbers x and y must be co-prime. So for example, if a form must represent a prime number p, can anyone tell me whether we can conclude that this representation should be proper or improper? Let's say your form is ax square plus bxy plus cy square, and it's representing a prime number p. Would anybody like to guess whether this would be a proper representation or not? Nobody. Okay, so is this in fact going to be a proper representation? Let's assume it's not. Let's say d is the GCD of x and y, and let's assume d is greater than 1. What this means is that d square will divide this entire thing because d divides x, so d square divides x square, d square divides xy, and d square divides y square. So this would imply that d square would divide p, but p is a prime number. So the only square of any number which can divide p is 1. So d must be 1, and hence the representation is proper. So we say f is positive definite, negative definite, or indefinite if f represents only positive numbers, only negative numbers, and all integers. All as in both signs, positive and negative. So for example, this form x square plus xy plus y square is positive definite, minus x square plus xy plus 1, negative definite. But yeah, so this is positive definite, and this form, let's say x square plus 5x plus y. So this is negative. This is indefinite. This can represent positive and negative number also. Okay. So now we'll talk about equivalence of binary quadratic forms. So we define an equivalence relation between binary quadratic forms as follows. we say f is equivalent to G if the matrix of f, which was given above. So let's say f is ABC, that is ax square plus bxy plus cy square. And the matrix of f was 2a, bb, 2c. We say f is equivalent to G if the matrix of f is similar to the matrix of T. Via this transformation, T in GL2Z, where GL2Z is the set of invertible 2 cross 2 matrices with integer entries. So this is the set of matrices PQRS, where PQRS is invertible. So as PQRS is invertible and it has integer entries, its determinant, its inverse is 1 by determinant of this times the adjoint of this. And for this to be an integer valued matrix, determinant of T has to be plus or minus 1. So for something to be in GL2Z, the determinant should be plus or minus. And if T is an SL2Z, that is matrices with determinant 1, then we say F is properly equivalent to G and denoted by F is equivalent plus D. So for example, x square plus y square is properly equivalent to 5x square plus 26x minus 34y square via the transformation x goes to 2x plus 5y and y goes to x plus 3y. So you can see that the matrix of this transformation is 2, 5, 1, 3 and its determinant is 1. So this is an example of proper equivalence. And yeah, as I said above in this example, the equivalence can also be restated like this. We say f is equivalent to G if and only if f of if and only if G can be obtained from f via a linear change of variables, where so this is saying that f of alpha x plus beta y comma gamma x plus delta y is G of x y, which alpha beta gamma delta indices, and the determinant of this is plus or minus 1. So what this is telling you is that you can invert this system of equations, so you can solve alpha x plus beta y and this equal to x dash y dash, and you can also invert this. So if you have alpha x dash plus this equal to this, you can get x from x dash y dash from xy and xy from x dash y, x dash and y dash. So we can check that this is an equivalence relation, and this definition above tells you that equivalent forms will represent the same integers, because if something is represented by G here, then you can represent it by F here just by substituting this change of variables and the same number of times as well. They also have the same discriminant. Why is this? So we have this equation here, MF equals T mg T inverse. If we take the determinant of both sides, we get determinant of MF equals determinant of T, determinant of mg, determinant of T inverse. T and T inverse determinant multiplies out to be 1. So determinant of MF equals determinant of mg, but this is minus discriminant and this is minus discriminant. So the discriminants of both of these are same. And also primitivity is invariant under equivalence. So if f is equivalent to G and f is primitive, then G also must be primitive. Okay, so now we will go ahead. If anybody has any doubts, please let me know and clarify. So now here are some theorems which talk about when certain numbers can be represented by quadratic forms. So the first theorem is here as follows. A form f of xy properly represents an integer m if and only if f is properly equivalent to mx square plus bxy plus cy square for some integers b and c. So what this is saying is that if you have some form fxy which represents m, that means that you can find some integers where x naught y naught such that f of x naught y naught is m, then via a suitable change of variables you can make f transform to g, where g has the leading coefficient as m. So g is mx square plus bxy plus cy square. Proof of this is not very hard, but we can do it towards the end if time is left. And the second theorem is here, that delta 0, 1 mod 4 be a discriminant and m be a non-zero integer. Delta is a square modulo m, which means that there exists some x such that x square is congruent to delta mod m. If and only if there is a binary quadratic form of discriminant delta properly representing m. So to prove this statement, we actually use this statement above, as you can understand. And yeah, if time permits, towards the end, we can look at this. And the corollary from this is that if delta is a discriminant and p is a prime such that the Legendre symbol of delta mod p is 1. So what this means is basically what I've said above. So let me just define this. This is the Legendre symbol. This is equal to 1 if there exists x such that x square is congruent to delta mod p. So what this means is that there is some x such that x square and delta leave the same remainder when you divide them by p, and minus 1 otherwise. So if some of you have seen quadratic reciprocity, you know what I'm talking about. Legendre symbol is used there. So the corollary is that if delta is a discriminant and p is a prime such that the Legendre symbol delta by p is 1, then there is a binary quadratic form of discriminant delta which properly represents p, which is unique up to equivalence. So this is also something that you can prove using these two results above. And now we come to reduced forms. So in defining the class group, we require the notion of reduced forms, and we'll define them as follows. And from here, we'll consider positive definite forms f, because for indefinite forms, the theory is a bit different and the definitions are somewhat complicated. So since the form is positive definite, the discriminant is strictly less than 0. And we define a form f equals ax square plus bxy plus cy square to be reduced if this condition holds true: mod b less than equal to mod less than equal to a less than equal to c, or if b is greater than z, if in the exceptional case that mod b equal to a or a equal to c, so b greater than 0. So if this happens or this happens, we define the form f to be reduced. So here are some examples. So what about this form, 2x square plus xy plus 4y square? Here a is equal to 2, b is equal to 1, and c is equal to 4. So clearly mod b is less than equal to a less than equal to c. So this is reduced. What about this? Here a is 3, b is minus 1, c is 7. Again here mod a, mod b which is 1 is less than equal to a which is 3 is less than equal to c which is 7. Here, so these two are reduced. This is not reduced because mod b is 5 here and a is 4 here. So mod b is greater than a, and this is not a reduced form. And this form is reduced because it satisfies this condition here. So this was just to get you familiar with some examples and the definition of a reduced form. Okay. So now we are in good shape after this theorem to define the class group. So we look at this theorem, which states that every primitive positive definite form is properly equivalent to a unique reduced form. So what this means is that if you have a positive definite form ax square plus bxy plus cy square, positive definite means b square minus 4ac is less than 0 and a is greater than 0. And primitive means that the GCD of all the coefficients a, b, c is 1. Then this is properly equivalent to some form dx square plus exy plus fy square, where this form is reduced. So it either satisfies this condition or the other condition. So the important thing here is the positive definiteness. This is not true if f is not positive definite. And the unique part is also important, that this reduced form here is actually unique. So perhaps we'll look at this proof. We look at only the existence part, and the other parts you can try on your own. So first step is to show that such a form is properly equivalent to one satisfying this. Okay. So you pick a form properly equivalent to f with mod b minimal. So if your f is cx square plus bx square plus ey square, we take a form ax square plus bxy plus cy square, which is properly equivalent to this. And this middle coefficient should be of minimum absolute value, minimum possible. Okay. And from here, if A is less than mod B, then we transform F using this matrix 1, M, 0, 1. So this matrix has determinant 1. So the transformation which we get by applying this matrix is G of xy, which is f of x plus my, comma y. So this, if you check, this would come out to be ax square plus 2am plus bxy plus c prime y square. So f of x here I'm taking ax square plus bxy plus cy square. And after applying this transformation, we get f to be equivalent to g, where g is of this form. So as a is less than mod b, you can choose an integer m such that this holds, right? So you can take m to be less than my mod minus b by 2 or something like that, and you can get that this will hold true. So, but this will contradict the choice of f, because we took f to be the form with mod b minimal. So we must have a greater than equal to mod b and c greater than equal to mod b similarly. If c is greater than equal to a, then we are done and the form is reduced, because it will satisfy this condition. Otherwise, a is bigger than c, and we can interchange coefficients via this matrix. So 0, minus 1, 1, 0. This matrix also has determinant 1. And this will transform your matrix to, if you swap the coefficients basically, a and c, and we get this relation, which is the reduced form. So here we have shown that this is equivalent to a reduced form, properly equivalent to a reduced form. And other parts of this you can check on your own. I mean, they are somewhat more computational, so we leave it here for now. But yeah, this is what the statement is, and this is very important, as we'll see here. So to define the class group, we'll note one thing first. So if f of xy, ax square plus bxy plus cy square is a reduced form of discriminant less than 0, then this condition mod be less than equal to a less than equal to c. Upon squaring, we get b square less than equal to a square less than equal to c square. And substituting these inequalities in this condition here, we get minus delta f, which is 4ac minus b square is greater than or equal to 3a square, right? Because 4ac minus b square is greater than or equal to 4a times a minus a square. This inequality sign flips. So this is 3a square. And from here we get a is less than equal to square root of minus discriminant by 3. So what this is telling you is that for a reduced form, the leading coefficient a has finitely many choices, right? Because this delta is bounded. So delta is fixed, so this a is bounded above, and a is positive because positive definite, so a has finitely many choices. And our condition before was mod b less than equal to a less than equal to c. So if a is bounded, then b is also bounded, because mod b bounded just means you get plus and minus signs. So b also has finitely many choices, and the discriminant is fixed. This is b square minus 4ac. So if you have a particular value of b and a particular value of a already, then your c is automatically decided by this discriminant delta. So what we have concluded is that if there is a reduced form of discriminant D, there are actually only finitely many reduced forms of discriminant D. Right. This is here. And thus the number of proper equivalence classes is also finite by the above theorem, because every primitive positive definite form was equivalent to a unique reduced form. So the proper number of proper equivalence classes is also finite. And we say two forms and the same class if they are properly equivalent. So this gives you the very important definition of class group, and it shows you that this is also finite. So if we let HD denote the number of classes of primitive positive definite forms of discriminant D less than 0, then as we have shown above, HD is finite, and this is equal to the number of reduced forms of discriminant D. We call HD the class number of forms of discriminant D. So this is one definition of the class number by looking at quadratic forms. And now we come to the problem which Gauss stated in his book Disquisitions Arithmeticae. So this was the book where Gauss collected works of his predecessors like Lagrange, Legendre, and Euler. He collected whatever they did and he added some of his stuff. So you all must have heard that when Gauss was a teenager, he conjectured the prime number theorem, that is, that number of primes less than equal to x are asymptotic to this x mod log x. And he also showed that the 17 gone, so this is a polygon with 17 sides, regular 17 one. This can be constructed using ruler and compass only. By ruler, I mean mark like a straight edge without any markings, just the unit length. So Gauss, in this book, this was basically his major book in which he wrote whatever he had done up until his mid 20s. And he made the following conjectures in this book. He wrote that HD goes to infinity as D goes to minus infinity. So what Gauss was saying is that as you decrease your discriminant down and down towards minus infinity, then the class number will increase to infinity. So this was proved by, I don't remember who, this was proved in early 1900s. And the second statement is called the class number one problem. So Gauss calculated that the class number was equal to 1 for these forms here, for these discriminants, sorry, minus 3, minus 4, minus 7, and so on. And he thought that these were the only discriminants because he calculated some more and he was able to see that no other discriminants are satisfying this sort of class number coming out to be 1. So he conjectured that these are the only ones for which the class number is 1. And he also conjectured that if D is bigger than 0, then there are infinitely many D with class number 1. This is still open. Nobody knows whether this is true or not. This is proven, this is proven. And for the second statement, you can check the only if part. So if D is one of these values, then so let's do one check. For example, let's say D is minus 19. Then a reduced form must have discriminant minus 19. So let's say our form is ax square plus bxy plus cy square. So discriminant is b square minus 4ac, which is minus 19. And we have this inequality. So from above, we had shown that a is less than equal to square root of minus discriminant by 3. This is root 19 by 3, which is approximately 2.4 something. So a is either 1 or 2. If a is equal to 1, then b square minus 4c is minus 19. And we also had this condition, remember, mod b is less than equal to a. So mod b is less than equal to 1. And this condition tells you that b must be odd. So b is plus or minus 1. And if you put that here, you get c is 5. So one form we get is x square plus xy plus 5y square plus minus, in fact, but these two forms are in the same class, you can check. And if we put a equal to 2, then we get b square minus 8c equal to minus 19. Or b square equal to 8c minus 19. But this is actually not possible because b is clearly odd from here. So if you take b to be 2j plus 1 and square it, you get 4j square plus 4j plus 1. This is 4j, j plus 1 plus 1, and j times j plus 1 is divisible by 2. So b square is 1 modulo 8, but this right hand side is 5 modulo 8. So they cannot be equal, and hence for minus 19 the class number is 1. You can also check for the other ones that the class number will come out to be 1. But showing that these are the only ones with class number 1, that was very difficult, and that was proven. Okay, and the story of that proof is in the next slide, as we'll see. So this is the story. Igner and Stark, they're two mathematicians. So actually, a supposed proof of the second statement, which is the class number 1 problem, this was published by Kurt Igner in 1952. So Kurt Igner was actually a radio engineer who was also dabbling into some mathematics along the way. So he was a radio engineer who published a proof of this problem, but his proof was supposed to contain a gap because some result that he had quoted was incorrect. And the first accepted proof of the class number 1 problem was given by Harold Stark in 1967. But when they later on checked Higner's proof properly, they saw that the gap was actually not that big. The gap could have been fixed, and the proof was essentially correct. There was no flaw. But it was sad that Higner passed away in 1965 without knowing that his proof was actually correct. So here is a photo of Higner and Stark. So this is Stark, and this is Higner. Stark is still alive, I believe. He is 99 years old. So, yeah. Now we come to the second part of the talk. So, in the first part, we talked about binary quadratic forms, and we developed what is known as the form class group, which was the group of reduced, so a group of primitive positive definite forms. Why that is a group actually is because there is the operation of composition which you can define on quadratic forms. I will not go into that. That is very rich topic with a lot of theory. So what that is basically is if you have two forms like this and another form like this, then you can compose them, whatever that means, to get another binary quadratic form which is also primitive. So if anybody is interested, they can read about composition of quadratic forms, and it can be shown that they are a group under this composition. There are some types of composition which have been defined. One is Gauss composition, and a slight modification of that was given by Dirichlet. And recently, Manjul Bhargava worked on the composition problem as well. His ideas were particularly innovative. So if anybody is interested, they can read about that. So for the second part, I will talk about quadratic extensions of Q. So does everybody here know some vector spaces, basic linear algebra, and some ring theory? Okay, it's okay. I'll try to not go into too much depth. So we begin with, obviously you all know that if this is a quadratic equation, then its roots are given by minus b plus minus square root of delta by 2a, where delta is the discriminant. So these are of the form clearly x plus y root delta with x comma y and q. So they are in this set q a joint square root of delta, which is the set x plus y root delta with x comma y integers. This is a subfield of C, as you can check. And this is also a vector space over Q with addition component wise and scalar multiplication. So if you do x plus y root delta plus z plus w root delta, you will land in this because this x plus z plus y plus w root delta. And scalar multiplication works like this. If you have lambda in Q and if you multiply it like this, you get lambda x plus lambda y and loop delta. This is rational, so you land up in that. And all of these are well distributed, so they satisfy the axioms of a vector space. And a Q basis of this would be 1 comma root delta, and Q is contained in this. So as a vector space over Q, this dimension of this set is 2. Okay, and now we'll talk about number fields. So a number field is a subfield K of the complex numbers, sorry, which is a finite dimensional vector space over Q. So what this means is that the dimension of K, if you see it as a Q vector space, this is some finite number n. And this dimension, which is denoted by this bracket K over Q, is called the degree of K over Q. And now here is a little exercise that a number field is algebraic, which means that every element of a number field satisfies some polynomial equation over Q. Okay, how do we prove this? Let me just show you. So let's assume that the degree is n. What this means is that any set of n plus 1 elements would have a linear dependence, right? Because a basis is a maximal linearly independent spanning set. So any set of n plus 1 elements would have to be linearly dependent. And if we consider this set 1 alpha alpha square and so on, so take any alpha in K and consider this set. This set has to be linearly dependent. This has n plus 1 elements, or you can continue. So this has to be linearly dependent. That means that there are constants ai such that ai summation ai alpha power I equals 0 to n is equal to 0 with not all ai equal to 0. So this is the polynomial which alpha will satisfy over Q. So every element of a number field is in fact algebraic. This is what it's called. That it satisfies its algebraic over Q. And this is also a fact that every number field is actually generated by one element over Q. So one second. Yeah, so what this says is that K is Q adjoint alpha for some alpha in K. So any number field is actually generated by one element over Q, and alpha will of course satisfy a polynomial of some minimal degree, and that polynomial is called a minimal polynomial, and its degree is actually equal to the degree of extension of K over Q. So this was a bit of introduction about number fields, and now we define the ring of integers of a number field. So the motivation for this kind of definition is that you have the integers sitting inside the rationals, and we want to get some set inside this number field K which is similar to the behavior of integers inside rationals. So what we want is like so any integer satisfies this polynomial x minus n equal to 0. So any element of this should satisfy some sort of integer polynomial. That is what we want. And also any element in Q can be written as a over b for some integers a and b. So we want any element of K to be written as a over b where a comma b are in OK and other similar things. So what we are doing by defining the ring of integers is that we are trying to create a subring inside this which behaves almost exactly like the integers behave inside the rationals. So that is called the ring of integers, and we define it to be the set of all elements of K satisfying monic polynomial equations over Z. So to write this down, OK is alpha in K such that x bar n plus a1 square minus 1 plus an equal to 0 alpha 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 n, where the ai's are integers. So this is what OK is, and OK is actually a ring. You can check that, and the proof is basically uses this statement that alpha is in A and only z of alpha is a binary generated z module if and only. Yeah, so using this you can check that alpha is the ring of integers actually a ring, and here are some parallels between the rings of integers of a number field and normal integers. So yeah, integer roots of monic polynomial, these are also roots of monic polynomial integer coefficients. The fraction field of z is q, the fraction field of OK is k. Z is a finitely generated Z module trivially, and OK is also a finitely generated Z module with rank equal to this k over q, and in Z, any ideal can be written as a product of prime ideals. This is also true in the ring of integers. This is not a trivial statement to prove. But unique factors and elements also holds in Z. That is, any integer is a product of non-zero integers, non-zero prime numbers in a unique way. But this is not true in ring of integers because Z of minus root 5, which is the ring of integers of Q of minus root 5. In that 6 is 2 times 3, which is 1 plus root 5, root minus 5 times 1 minus root minus 5. Okay, so this was something about ring of integers, and we define a fundamental discriminant, which is a discriminant which is either odd and square free, or it is, if it is even, then it is the quotient of it by 4 is 2 or 3, not 4. So this is in some sense like restricted the number of squares that can occur in its factorization. And here we show that the ring of integers is in fact a ring. This is just calculation, you all can look at this, and in general, if your k is q adjoint square root of delta, then the ring of integers OK is actually this z adjoint delta plus root delta by 2. And you can also show that the field of fractions of OK is k. So let me try. Okay, we'll do that at the end of this time. And we look at some ideal theory. This is, I don't want to go too much into theory because there's not much time. So yeah, this is what an ideal is. An ideal is a subset of a commutative ring R if it is an abelian group under addition, and Ri is an I for all R in R and I in I. So basically, if you multiply any element of I with any element of R, the end result should land in I. And you can check that all ideals of Z are given by NZ by the remainder theorem. Remainder theorem, sorry, Euclid's lemma, Euclid's division lemma. Yeah. And we say an ideal is generated by R1, R2, Rn if any element in I can be written as a linear combination of elements in the ideal R1, R2, and Rn. We write I to be R1, R2, Rn. So for example, in Z, in Z, if I look at ideal generated by 2, 5, this is set of elements 2x plus 5y where x and y are integers. And this set is in fact Z itself, because 1 is in this set, because 1 is 5 plus 2 times minus 2. And since 1 is in this set, any multiple of 1 is in this set, because you can write any integer n as 2 times minus 2 and plus 5 times n. So yeah, this is ideals, and some kinds of ideals which are prime ideals and maximal ideals. So a ideal I is called a prime ideal if product of two numbers in I implies that one of them should be in I. So one example of this is p times z, where p is a prime in z. So this is the motivation for defining a prime ideal, that it mimics the prime numbers in z. Because if a prime number divides the product of two numbers, then we know that it should divide either one of these by Bezout's lemma and similar arguments. And we call an ideal I maximal if there is no other proper ideal containing it. So if there is some ideal J which contains I, then either J should be equal to I or J should be the entire ring. Again, another example of a maximal ideal in Z is PZ for P prime, and these are the only maximal ideals. Because if your N was composite, you can write it as AB times, you can write NZ as AB times Z, with A comma B bigger than 1, and this would be strictly inside AZ, which is not the entire ring. So yeah, and this you all must have seen if you have done ring theory, that I is prime ideal if and only if the quotient R mod I is an integral domain, and I is maximal if and only if the quotient R mod I is a field. Now we talk about factorization and general rings. So these are some definitions which mimic the properties of integers. We call element U in our unit if there is a V such that UV is 1. So these are the invertible elements under multiplication, and they form a subgroup of R which is denoted by R star. So units in Z are plus minus 1, units in Z I are plus minus 1 and plus minus I, and so on. And we call A comma B associates if A is B times U for some U in R. So in Z, A and plus minus A are A and minus A are associates because they are differ by minus 1. And in ZI, 1, A and minus A and plus minus AI are all associates. And we say A divides B if there is a C in R such that B equals AC. So in ZI, for example, 1 plus I divides 2I. So 1 plus I divides 2 as 2 is equal to 1 plus I times 1 plus I times minus I. So 1 plus I times some element is 2. So 1 plus I divides 2. And an element is called irreducible if we cannot break it down. What that means is if pi is AB for some A and B in R, then either A or B must be a unit. For example, any prime in Z, right? Because if you try to write a prime number as product of two integers, then of course one of those must be plus or minus 1. Okay. And we call pi not prime if pi times R is a prime ideal. So this is the ideal generated by pi, which is the set of pi x, where x is an R. Equivalently, we can show that pi is prime if and only if pi divides AB implies pi divides A or pi divides B. So this is the generalization of prime numbers in a general ring. And it can be shown in an integral domain, which is a ring with no zero divisors. What that means is if product of two numbers is zero, then one of them must be zero. So any number field is an integral domain. Example of set which is not an integral domain is matrices, because you can have two non-trivial matrices to multiply to the zero matrix. So in an integral domain, any prime is irreducible, but the vice versa might not be true. Okay, so let's talk about unique factorization domains. These are rings where every non-zero non-unit can be written as a product of irreducibles in a unique way up to the ordering and associates. One example is integers, because by the fundamental theorem of arithmetic, every integer a is a product of pi e to the I, where pi's are primes, and this is unique up to reordering. So what that means is if you have p1, e1, and pn, en, you can change the order. You can write this as p1, e1, pn, en, p2, e2, and so on. And you can also write plus minus 1 here, plus minus 1 here. So up to reordering and associates, this factorization is unique. What is also true is that every PID is a UFD, so every principal ideal domain, which means that a ring in which every ideal can be generated by one element. This is a unique factorization domain, but the converse is not true. So, yeah. And also, Z root minus 5 is not a UFD, as 6 is 2 times 3. which is 1 plus root minus 5 times 1 minus root minus 5. And all of these are irreducibles. How would we check that? You can check that by defining a norm on this, which is similar to the norm of the complex numbers. Not similar, it's exactly the same. So norm of a plus b root minus 5, if we define as a square plus 5b square, and we can check that 2 and 3 are irreducible if you try to write 2 as xy. And you can also check that an element is a unit if and only if its norm is 1. So if you try to write 2 as xy, then norm of 2, which is 4, would be norm of x times norm of y. And norm is, of course, non-negative. And norm of x times norm of y is 4 means that either norm of x is 1 or norm of x is 2 or norm of y is 1 or norm of y is 2. But if norm of x is 1, then x is a unit by this. So the factorization would give a unit, and the norm cannot be 2 because a square plus 5b square equal to 2 has no integer solutions. So you can check that 2 is irreducible and so is 3 and the other two numbers here. So this is a factorization into irreducibles in different ways, and these are not associates as well because they have different norms. So this shows that Z with math is not UMD. And I'll skip this for now, I think, but you can read that in the slides later. So if I and J are ideals, you can define their sum I plus J to be the set I plus J, where I is in I and J is in J. This is an ideal because R times any element of the set is Ri plus Rj, and Ri is in I. So sum I prime and Rj is in J, so this is some J prime. So this is also an I plus J. And the Boolean gives that. And you can define the product. The product is not I times J for I nine J and J. It is finite sums of this form. So it is sum k equals 1 to n I k j k, where I k is in I and j k is in J, and n is a natural number. And this is a side that there was an effort to prove Fermat's last theorem using factorization in cyclotomic fields. So what that means is if you have zeta p, where zeta p is the nth root of unity, then you can factor this equation in zeta p. And if zeta p had some sort of, if this ring q zeta p or z zeta p had some sort of factorization, then we could try some sort of descent argument to prove Fermat's last theorem. But this is not actually true for all p. In particular, for p equals 23 and 37, this does not have unique factorization. Okay. But what is very good is that ideals can be uniquely factorized. So any ideal in the ring of integers can be written as a product of prime ideals up to reordering and associates. So for example, we had above 6 was 2 times 3, this and this, and this times this. But if we write the ideal 6, if we try to factorize that, then if you take p to be the ideal 2 comma 1 plus root minus 5, q to be 3 comma 1 plus root minus 5, and r to be 3 comma 1 minus root minus 5, then you can check that this factorization 6 equals this times this and this times this is actually equal to, so this is actually p square. So when you square this ideal, you get ideal generated by 2, and if you do q times r, ideal generated by like the product of these two, then you get 3. So p square qr is equal to 6, ideal by n by 6. And here you can check that this is actually pq and this is actually pr. So this is also p square qr. The only thing is it has been reordered. So this factorization of elements, which was not unique, is giving us a unique factorization of ideals up to reordering. And this tells you that if you have a good look at the ideals, then perhaps you can understand more about the number rings. And I'll end shortly. So we want to also measure how far this ring of integers is from being a PID or a unique factorization domain. And to check that, we define the ideal class group. So the ideal class group is defined like this. If I is the set of ideals, then an equivalence relation is defined we say two ideals A and B are equivalent if they are same up to multiplication by element of OK. So what that means is that if there is alpha and beta such that alpha, the ideal generated by alpha times A is beta times B, then we say that these two are equivalent. So up to multiplication by an element, if they are the same, then we say they're equivalent. And this induces a product on this as this, and this product is well defined, which you can check. The catch is that this is actually a group. This operation is a group. It defines a group operation that is not non-trivial. That's not trivial to check. And you can also show that this class group is one, means that every ideal is principal here. So this is clear. And OK is actually what is called a Dedekind domain. And in such domains, the property of being a PID and a UFD is actually the same. So we get this equivalence. So yeah, this class group is important because if the class group size is 1, that is when it is a UFD. And if the ring of integers is a UFD, then the class group size is 1. So this tells you sort of how to measure whether there's unique factorization. And as I said, this is a very deep result to prove that this class group is finite. We use Minkowski's theorem and other things to check that. So this is the main theorem. Now, one side of the talk, we talked about class groups of quadratic forms. And in the other side of the talk, we talked about the ideal class group. What is very surprising is that these two are actually the same. What that means is that if you have a discriminant, I don't think it's fundamental, but I'll have to check. So if there's a fundamental discriminant delta less than 0 and k is q root delta, then the map sending a primitive positive definite form to this ideal induces an isomorphism between the class group and the ideal class group. What this means is that the group we were looking at before, like HD, the class group of reduced forms, this is actually isomorphic to the ideal class group. So what this means is that you have two very different perspectives. One, you look at quadratic forms, reduced forms, and in the other, you're looking at ideals, quotienting, and stuff like that. But these two are actually the same. So this was what I had to tell you today. And yeah, this numbers that actually occur here 2, 3, 5, 7, and 1741. If you do 1 minus 4c, then you get q root minus 7, q root minus 11, q root minus 19, q root minus 67, q root minus 163, and these are actually the number fields with class number 1. So this polynomial being prime is very closely related to the class number of the quadratic fields being 1. And as we know that these are the only ones where the class number is 1, so this polynomial n square minus n plus 41 was actually the biggest example of such a polynomial. And finally, I'd like to end my talk with the following quote by Poincaré, which says that mathematics is the art of giving the same name to different things. So we studied one thing quadratic forms, other thing extensions of Q, and realized that these two actually give us the same information. And that's all. Thank you.
So if anyone has any questions, if there are no doubts, then we can thank our speaker once again. So thank you, Gauransh, for the talk. We can conclude the meeting.
Okay, thank you. Bye bye.
Again.